Hello everyone and welcome back. In this video, we are going to look at calculating the net gravitational force acting on something. So we've been talking about Newton's universal law of gravitation. So I'm going to write that equation up here on the top. The gravitational force of attraction between any two masses is equal to G times the mass of the first object, mass of the second, divided by the distance between them. So we might calculate the force of attraction between you and your neighbor. We might find the force of attraction between you and the earth, or the force of attraction between a calculator and a pencil. But in real life, it is unlikely that there's only two objects in the story. So for example, the moon is attracted to the sun and the earth at the same time. Technically, the moon is attracted to the sun, the earth, and all the planets, and the calculator, and you, and everything. And so everything is attracted to everything else. So there's an unlimited number of masses in every story. So instead, we simplify our story by just isolating the two masses. What is the gravitational force of attraction between you and your neighbor? In this lesson, we are going to have more than one mass in our story, but we're still going to isolate a system so that it's small enough for us to be able to figure out the net gravitational force. So the net gravitational force acting on a series of masses is going to be the vector sum of the gravitational forces of attraction between each of the respective objects. So for example, here's a picture. We have a 5 kilogram mass, a 0.1 kilogram mass, and a 10 kilogram mass. They're all attracted to each other. So the question is, calculate the net gravitational force acting on the 0.1 kilogram mass. So I always like to circle who I'm focusing on. I'm focusing on him. So this mass is attracted to this mass, and this mass is attracted to this mass. So I'm going to start by number crunching the force of attraction between these two. So that gravitational force of attraction would be equal to G, 6.67, times 10 to the minus 11, times the mass of the first object, that would be 5, times the mass of the second, that would be 0.1, and the distance between them, the distance always has to be in meters, so that's going to be 0.4 squared. And then I'm going to number crunch that. Unfortunately, with a number like 6.67 to the negative 11th, I always get ugly answers. And so that turns out to be 2.08 times 10 to the negative 10 newtons. So not a super strong gravitational force of attraction between these two. And by the way, the gravitational force of attraction is equal and opposite. So he is attracted to the 5 with this force, and the 5 is attracted to him with the same value. But we're talking about this mass. All right, so this mass is also attracted to this other mass. So I'm going to number crunch that. So now I'm going to focus on these two. And so that's going to turn out to be 6.67 times 10 to the minus 11. And we have the 0.1 and we have a 10. So it's more massive, but he also is farther apart. And then I have to square that. So maybe his force of attraction is not as much as we think. So I number crunched that, and I got 1.85 times 10 to the negative 10 newtons. All right, so I'm going to circle this answer, and I'm going to circle this answer. All right, and then what I do is I come back to isolate this, say, okay, I'm talking about this mass right here. I'm just going to draw him here. And he is attracted to this guy with 2.08 to the negative 10. So I'm going to make that kind of like a long arrow. I'm going to call it the big arrow. So this is 2.08 times 10 to the negative 10. And he's attracted to this guy less. So I'm going to make his arrow shorter. And I'm going to write down 1.85 times 10 to the minus 10. So I called this a linear example because all of my masses were in a straight line, which means that I can just subtract the big arrow minus the little arrow to find the net force of attraction. So the net force of attraction is going to be a little bit going to the left. And when I subtracted those two numbers, 2.08 times 10 to the negative 10 minus 1.85 to the negative 10, I got 2.3. So the net gravitational force, I'm going to put the word net here, is equal to 2.3 times 10 to the negative 11 newtons. All right, but let's look at another example now where the objects are not in a straight line. So this is a very simplified picture, but over here we have the sun, and we have the moon, and we have the earth. So in this exact moment, they're in this, I'll call it right triangle configuration. All right, so it says calculate the net force acting on the moon due to the gravitational attraction to both the sun and the earth, assuming they're at right angles to each other. And then we're given some data down here. All right, so this time I'm focusing on the moon. So I'm going to circle the moon. And I'm going to say to myself, well, the moon is attracted to the sun, and the moon is attracted to the earth. So I'm going to number crunch those values to start with. So let's do the sun and the moon. So that's going to be 6.67 times 10 to the minus 11 times the mass of the sun, 1.99 times 10 to the 30th, times the mass of the moon, 7.35, times 10 to the 22, and divided by how far apart the average distance between the sun and the moon if I turned them both into point masses. That would be 1.5 times 10 to the 11, and then I got to square that. All right, let's figure out what that equals. Let's see if that shows. I think it does. All right, so we got 6.67 to the negative 11. Showing on my screen, yep, times 1.99 e to the 30th times 7.35 to the 22nd. There's my numerator divided by parenthesis 1.5 e to the 11, and then I got to square that. And I'm going to call that 4.3 to the 20th. 4.3 times 10 to the 20th newtons. All right, that's the gravitational force of attraction between the sun and the moon. Now, let's do the gravitational force of attraction from the moon to the earth. So that's going to turn out to be 6.67 times 10 to the minus 11. I can already see I'm going to run out of space. So I'm going to start to write small. 5.98 to the 24th. That's the earth. And the moon is 7.35 times 10 to the 22nd. And on average, if I turn them into dots, the average distance is 3.8 times 10 to the 8th. And then I got to square that. All right, so we get 6.67 to the negative 11th times 5.98 to the 24 times 7.35 to the 22 divided by 3.8 to the It's an 8. It's an 8 squared. 2.03 to the 20th equals 2.03 times 10 to the 20th newtons. And again, please take the time to number crunch that yourself, because that's one of the common mistakes that happens. All right, so now let's map out what we just found. So I'm going to redraw my picture over here. So this is the moon. And the moon is attracted to the sun. That's the bigger number. So I'm going to make this arrow longer. So the moon is attracted to the sun with a gravitational force of 4.3 times 10 to the 20th. And at the same time, he's attracted to the moon, or I'm sorry, the moon is attracted to the earth in this direction with a smaller number. So I made that arrow smaller. So we're just doing vector addition here. And because this is a right triangle, I'm going to make a parallelogram. And the Earth then is going to accelerate in the direction of the net force. So the moon is going to be pulled in this direction. I'm going to call that C. So I'm just going to do some a squared plus b squared. We use Pythagorean theorem here. So I'm going to clear all that out of my calculator. So I am going to be introducing some round off error here, but that's okay. 4.3 to the 20th. So I'm going to clear that. I'm going to use parentheses. This old calculator needs parentheses. 20th parentheses squared plus 2.03 to the 20th squared equals, then I'm going to square root that, and 4.8. So the net gravitational force, I'll say net. Whoops, that's off my screen. Hold on one sec. So the net gravitational force is equal to 4.8 times 10 to the 20th newtons. And we will see that the moon is going to be going off at this angle, which we'll call theta, so many degrees south of west. And we can just use sine, cosine, or tangent in order to find that value. I'll save that step here. I think you know how to do that. And we get 24.5 degrees south of west. So another thing that we need to be able to do is use this equation and apply it when we have more than one mass in a linear fashion or at right angles. And so I think you can see how to hook that together with an old topic. And I think that we are done with this video. So I'll see you next time.